Okay, thank you. And thank you for inviting me to the summer school, the organizer, for to have that opportunity to talk about this. So basically, I'll try to take it from where Martin stopped at the Nonlinear Schrödinger equation, the NLSE as it's called, to the Lugiato-Lefever equation, which describes the soliton, which underline frequency combs. And so I'll start from the basics of the Martin introduced a resonator. I'll look at what happens when you put the nonlinearity into the resonator. I'll briefly touch about how we describe this mean field model, this Lugiato-Lefever equation, which I'm sure you have heard of, and then we'll talk about modulation, stability, and how it leads to solitons. So this is the system we are looking at when we talk about microcomb, and just to give you a bit of a history, you probably know that combs are important. They have all these applications you're trying to develop. And the thing is that when they were first discovered, as Scott explained yesterday, it was based on mode-lock laser, these very large bulky system and so on. And in 2007, there was a bit of a strong interest, because people discovered you could generate these combs out of these micro resonator. And that came a bit of a surprise. Now, this is 2007. For my PhD thesis, which was pre-2000, I've actually been studying fiber optic resonators, which basically have the same shape as these microdiscs. They're just much larger, like 100-meter long. But they are basically the same ingredients. We have the K nonlinearity. This was silica in this 2007 experiment with silica fiber. And light is going round and round. So you can see that it's a totally different scale, 100-meter loop versus 100-micron resonator or what. But basically, there was some strong connection there. And it took the time to connect the dots, but sort of my background sort of helped me move into the and help the development in that direction. And so basically, the key ingredients here that we have is that we have, first of all, I'd like to insist I will restrict myself to passive resonator. I know that some recent experiment, people try to put amplifiers in there and dope these things with erbium and whatnot. So I will stay passive here. So this is purely passive. It's not a laser. We have a lot of trouble with reviewer when we submit paper. They say, oh, this has been done in lasers already, but we have to insist that it's not a laser. There's no amplifier. It's entirely driven by this external laser. And because of the coherence, it's being said to be coherently driven. The key ingredient is that we have dispersion and nonlinearity, and the third one is feedback. Okay, the light that's in there sort of loops back. And so you have this combination of dispersion, nonlinearity, and feedback. And that give you some reasonably complex behavior. And in fact, this has been called the hydrogen atom of nonlinear cavity, or the paradigm of optical systems subject to instability. Because, on paper, it looks very simple. Okay, you take a material, you make a loop, and you have all these things that happen. Here also put that it's purely one-dimensional. I'll look purely at the temporal dynamics. But of course, in some more complex micro-resonator, you could have spatial mode and so on, but I'm not going to look at that. Credit where credit is due. A lot of the physics that's involved were actually developed even before me and before fiber in this sort of two-dimensional planar resonator. So basically, they had a nonlinear material in between two mirrors, and you shine a plane wave, and you get spatial dynamics instead of temporal dynamics. And this goes back all the way to the 80s. Okay, so the micro-resonator and soliton and comb physics didn't really start in 2010 or 2007. There's this whole background of result that sort of predates that, and that can be quite very important. And basically what happened is that dispersion is the word of the day, I think, but in this system, dispersion is not important. It's replaced by diffraction, okay, which is sort of the spatial equivalent. And in terms of experiment, there's some complication in the fact that quite often these planar resonators are not totally planar. The two mirrors may not be totally parallel, and it creates some challenges. But there was a lot of experiment being done in that field. So Martin introduced the idea that this loop, it's a Fabry-Perot, it's a ring resonator. It has these resonances, and it's described by this equation there. And here I'm writing this equation in terms of this parameter phi naught, which I call the linear cavity round-trip phase shift. Very long sentence, but basically it's the phase accumulated by the field over one round trip. And when this phase is a multiple of 2 pi, you get constrictive interference and get these peaks in the intracavity power. P is the intracavity power there. In terms of notation, there are going to be some equation I'm going to flash. The one important parameter I introduced is this alpha parameter, which I call it the overall cavity loss. It's actually half the cavity loss. So theta is the fraction of power that goes through the coupling here. And alpha IL are the internal loss. It's a fraction of power that is absorbed over one round trip. So alpha is kind of half those loss. And critical coupling, which you may have heard of, is obtained when alpha equals theta. Okay. Now, this linear cavity round trip phase shift, it's proportional to frequency. So we could plot the same function here in terms of frequency. And then these resonances, which are equispaced, would be equispaced by a certain frequency spacing. And that's the so-called free spectral range, which is 1 over the round trip time. And then Martin nicely introduced the finesse, which is the free spectral range divided by the line width, and the Q factor, which is the frequency of the resonance divided by the line width. So 2 different metrics to measure the line width. I like the finesse better in terms of nonlinear effects because it's basically the intracavity power when you get this confinement. The intracavity power at the resonance is essentially the finesse times the driving power to within some factor. Okay, so you can see that the finesse really tells you how much the power is enhanced in the resonator. And also the finesse has the advantage that it only depends on the loss and on nothing else. Well, the Q factor also depends on free spectral range. And so people often, they insist on how large the Q is, right, in these micro-resonator, very high purity material, and so on and so on. But if you take a very, very long fiber resonator, the free spectral range is very small. You can get a very large Q as well with much larger loss, okay? So it's not necessarily metric. The 2 metrics have their advantage, I guess. Now, what happens when you put the nonlinearity in there? Martin explained that when you have this self-phase modulation, the power of the beam introduces an extra nonlinear phase shift, which we can write in terms of this gamma coefficient that Martin introduced. And so the nonlinear phase shift is gamma times the length of the round trip, L times the intracavity power P. And basically what happens in terms of equation is that the equation for the Fabry-Perot, instead of being this function of phi naught, it becomes this function of total phase, and the total phase is, is the phi naught, the linear phase, plus the nonlinear contribution. And the result is that these resonance tilts typically towards the left, because gamma is usually positive. So why does that happen? So we can look at that in a bit more sort of on a grander scale, let's say on a bigger picture. Let's imagine we start here. So phi naught is proportional to your laser frequency. So you can change phi naught by tuning your laser. And let's imagine we're coming from the left, increasing the frequency, and I'm here at the bottom there. And now imagine that I increase phi naught a little bit by pushing my laser a little bit to the blue. So I'm approaching the resonance, because I put myself before the resonance, so I'm approaching the resonance. As I approach the resonance, well, what happens when you approach a resonance? The power goes up. If the power goes up, the nonlinear phase shift increases, and that essentially pushes you even closer to the resonance, okay? So you get sort of reinforcement of positive feedback effect. And so you can see it because of that, we're approaching the resonance faster. It's accelerated, and that explains the tilt, okay? And if you tilt strong enough, then you get this sort of folding effect. And you can see that for some range of parameter, we can have 2 or even 3 different solutions. So we get this multi-stability that shows up. Okay, it's called bistability because the middle one isn't stable, so there's only 2 stable ones. There is a nice geometric interpretation of that thing. Let's imagine I go back to this function again. We described the resonance of the Fabry-Perot. And so here in the previous slide, I was plotting it versus this linear round-trip phase shift, the phi naught, which is only a part of the total phase, right? But now imagine that I'm just plotting it on my graph. I plotted versus total phase. And now it looks exactly like the linear Fabry-Perot, okay? But keep in mind that we have the total phase depends on the power, and on the vertical axis also have the power, okay? Now with the equation for the total phase depends on the power. Well, I can solve for the power in that equation. And if I divide by the input power, I can get a second equation for this ratio of intracavity power over input power. And clearly, both equations have to be satisfied. And so graphically, we'll find a solution where these 2 equations intersect, okay? So the top one is this one. The bottom one, if you think about it in terms of a relation with respect to the total phase, this is a linear relation in terms of total phase. So it describes just a straight line, okay, whose x-intercept is the linear phase phi naught, and whose slope depends on the input power. And the larger the power, the smaller the slope, the more these lines tilt, okay? And so the solution is at the intersection of these things. So if I vary my driving frequency, if I vary phi naught, these lines slides along, okay? You can see 4 of them here. You can see the intersection, and this gives you this tilted resonance. You can see why it's tilted. It's because my orange lines are tilted because of the power. If the power gets larger, the slope of these lines gets smaller. These lines sort of lie down essentially, and you can have range of linear phase here, phi naught, where we get these multiple intersections, okay? And that's why we get this sloping effect, okay? Yeah, all the intermediate case, and in the limit of 0 power, 0 input power, these lines have infinite slope, they're vertical, and you just get the same resonance. That's the linear case, okay? But so you can see that there is sort of a threshold of power before you get to the situation where you have this free intersection. Basically, the slope of this orange line need to be at least, or need to be smaller than the largest slope of the green resonance. You can do the same argument for a fixed value of this linear phase and just varying the driving power. So if I put myself, say, initially on resonance at 0 power, I get this vertical line. As I increase my driving power, I change my slope. The line sort of tilts to the right. You can see different intersections there. And if you plot just intracavity power versus input power, this is the ratio of P over Pn. So we multiply by Pn, we get a line like that. And if I start with a linear phase, which is to the left side of the resonance, then I can get again the situation where I have free intersection. And then you get a curve like that, this S-shaped curve, which is typical of hysteresis, okay? Again, this is versus input power here, while this is versus this linear phase, but they're two sort of same side of the same coin, if you like. An interesting thing to observe is that here we didn't have 3 intersections, okay? We need to be sufficiently detuned to the left to have these 3 intersections. So you can see that there is a threshold of detuning. You need to be off resonant by a certain amount before you see this effect. And it's to the left, okay? And so that's why we usually count the detuning positive to the left, okay? And so that's why there's this minus sign there if you wonder about that. Okay, these are some early pics of optical bistability that I measured in my thesis back in 1998. You can see here we scan the resonance in one direction, in the other, and we can see the different height as we go up there and all the way back up as we go in the other direction. And this is this picture there. So just a bit of a trip down memory lane, I guess. Now, how do we get to the mean field model from that? Martin has shown you the nonlinear Schrödinger equation with those dispersion. He introduced you to this beta 2 coefficient, which describes dispersion. There is also beta 0 and beta 1. Beta 0 connects you to this linear phase I've been talking about for 10 minutes. Beta 1 is the inverse of the group velocity. And if you times that by the cavity length, this is your round trip time. This is the 1 over the free spectral range. So you can see beta naught is related to phi naught. Beta 1 is the free spectral range. Beta 2 is the dispersion, okay? Sometimes you can have extra terms in the, I'll skip a little bit over that, but sometimes you get we're going to talk about solitons. You have to keep in mind that the beta 1 there is the group velocity at the driving wavelength. But it may happen that your soliton is traveling at a different group velocity. And so because of that, you may introduce extra term in this equation like this one, or third order dispersion, or Raman scattering, and so on. But I'll show you what a general way of treating these terms in going to the LLE, the Lugiato-Lefever equation. So the equation here describes what happens as you propagate along the waveguide. Okay, we still have to take into account what happens inside this coupler, okay, at the boundary condition. And so we need a second equation here, and this is the one here. Don't worry too much about it. What it really says is that we take the field at the end of the round trip at position L, okay, that we obtain after integrating this equation. And then we take into account the the linear phase phi naught, which is not in this equation. We have to put it explicitly in there. And we have all the loss, you know, some of the light is lost through the coupler, some of the light is absorbed. And then we add what's coming in from the driving laser. Okay, so it's basically the end of the round trip, loss detuning, and what's coming in. Okay, and that's the boundary condition. Now, in the early days of Coen modeling from 2007, people were simulating exactly that. Okay, you start from initial condition, integrate the NLSE, apply this condition, integrate again, apply the condition, integrate again, and so on and so on. But microresonator is this very large Q, very large finesse, and as Martin explained, that means you need a lot of round trips before anything substantial happens. And so you spend a lot of time doing that, and it's not very efficient. And so but the fact that in high finesse resonator where the losses are very small, the point is that over a single round trip, nothing much happens. Okay, there's only so much power that's leaving the coupler, so your field can only vary by a small fraction of a single round trip. And so the idea is to say this is a small quantity. We're going to average over many round trips to some sort of average description. And this is what the mean field or the LLE model is about. Okay, and so we work in this so-called good capital limit, which is valid for large finesse. And mathematically, that means we assume that internal loss, coupler loss, detuning, they are all much smaller than 1. You might be wondering why the detuning? Well, we are trying to get this nonlinear effect, so we need to be close to resonance. If the finesse is very large, the resonance is very narrow, so your detuning is going to be small. Okay? If your detuning is large, you are far away from resonance, there is no power in the resonator, there is no nonlinear effect, and it's not interesting. And so under this approximation, the evolution of the field from one round trip to the next is going to be much smaller than 1 as well, and so on. So under this approximation, I'll go through that quickly. You can read about that in the literature, but the idea is that over one round trip, nothing much happens. So to integrate the NLSE, I just assume this derivative to be constant along the round trip, times by my resonator length. And this is basically zeroth order Euler integration, if you like. And then in the boundary condition, all of these small terms, we linearize all that, okay? And then we combine the two together, and all of these things in yellow, they are small, okay? And we only keep first order term, okay? And basically that means that obviously we're going to have a term alpha times, say, gamma LE squared, but that second order we neglect, okay? So we only keep the first order term. And the result is that what we get at the end, we can see the loss here, alpha, we can see the detuning, and we can see the driving. That's coming from the boundary conditions, okay? And then we have the nonlinearity and the dispersion. That's coming from the NLSE. But because we are only keeping this first order term, you can notice that in terms of what's coming from the NLSE, we get the very same term as above, except they have been multiplied by the cavity length, okay? So instead of beta 2 second derivative, we have beta 2L second derivative. And so you can see that if you fancy adding terms to the original nonlinear Schrödinger equation, like Raman scattering, a third order dispersion, or whatnot, in the LLE, they'll just appear as this very same term times L. Okay, easy as. So you can easily generalize the LLE by adding those terms times L. Okay. Now, what we have here is sort of the difference between the field at round trip m plus 1 and the field at round trips m. And all these things are small, okay, in this sort of high finesse, good capital limit. And so we can, if I divide this difference by the round trip time, this is essentially very close to a time derivative of the field over one round trip, if we sort of move to a continuous description, okay? And so what we do very boldly is that we're going to say this difference is equal to a slow time derivative of the field times the round trip time, okay? And this is where the slow times enter into the picture. And so the slow time is measure things at the scale round trip to round trip, while the tau parameter that I here describe the time at the scale or inside a round trip, inside a pulse structure, for example. And the nice thing about that, and so basically then this left-hand side here, which is a difference, it becomes a time derivative, and you go from a recurrence map, these two equations we had at the beginning, to a partial differential equation, which is much easier to handle mathematically. And this is the Lugiato-Lefever equations. Just a few words about the Lugiato-Lefever equation. In case you wonder what they look like, this is Lugiato and Lefever. Lugiato is an Italian physicist. Lefever is a Belgian physicist, happened to be from Belgium. He was from the university where I did my PhD, so I actually met I actually met both. Now, in terms of the sort of a form of this equation, it's a complex equation, it's a wave equation, but it relates to equations that have been derived in chemistry and in similar sort of fields by this fellow here, Professor Prigogine, which is also from my original university in Brussels. He got the Nobel Prize in chemistry to predict the existence of what we now call dissipative structure, okay, which are all these patterns that appear in nature, like zebra stripes, and you can think of plenty of other sort of patterns, okay? And before him, you know, Alan Turing predicted also the existence of patterns in nature in the context of chemical systems. So it's not exactly the same equation. Here we deal with real equation. This one is complex, but there's a kind of this notion of reaction diffusion equation is closely related to that, okay? Now, what we can look at this equation, one thing I like to look at is that if you neglect every single term but the loss, okay, the loss is this alpha here, what this equation tells you is that the power is going to decrease exponentially over a certain time scale. And this time scale is given by is so-called this photon lifetime, it's this TPH here, okay? And so if you know about ring-down spectroscopy, you know, you load a resonator and then you shut off the driving and you look at what time it decays. That's this time scale, okay? And it's related to the Q. The Q is the resonance frequency times the photon lifetime. And the photon lifetime is a good measure of how fast things evolve in the resonator, okay? And you can see that it's roughly given by the finesse times the round trip time. So roughly speaking, to have a large change in the field amplitude in the resonator, you need a number of round trip which is about the finesse, okay? And again, it comes from this idea that over one round trip, nothing much happens. You need at least finesse round trip for something substantial to happen. And that's why simulating the resonator using the recurrence map in a micro resonator is very slow, because you need thousands and thousands of round trip before anything substantial happens. Okay. While in this equation, everything is averaged out. You can actually use an integration step which is larger than the round trip time. Okay. The other thing I'd like to look at is that if we neglect the nonlinearity and the dispersion, and we look at stationary solution, so we're basically trying to go back to this resonance of the fabric pair I showed before. This is the equation that we get, okay? And what's interesting is that if you look at the green expression, this is a single Lorentzian line shape, okay? And that might be a bit puzzling. Essentially, it says that we started from a fabric pair that is these periodic resonances, and the Lugiato-Lefever equation only describes you a single resonance. And so that might be surprising. You might be wondering, how can we describe these combs that have all these frequencies matching all these adjacent resonances if the model, the LLE, only describes a single resonance, okay? And so just to understand that, here I'm plotting these resonances in terms of this phase, okay? That depends on frequency with the beta 1 and then the dispersion and so on, okay? And so let's imagine I have a comb of frequencies that is spaced by the free spectral range, and they are all, and if I neglect dispersion, as I shift from one resonance to the next by one free spectral range, I'm adding 2 pi of phase. And so in terms of the phase here, it's strictly periodic. And so if one is on resonance, they are all on resonance. These are these dashed blue line, okay? Now, if I add dispersion to this picture, if I add beta 2, you can see that for when omega is equal to the free spectral range, I'm adding a small term. When omega is twice the free spectral range, I'm adding a larger term. And so we get these green lines, okay? The central one is still on resonance. The first one is a little bit out of resonance because of the dispersion. The second one is further out because beta 2 omega squared for omega twice the free spectral range is even larger. And so you can see that progressively they sort of slip out of resonance, okay? And this is what would happen if you launch a frequency comb, equidistant frequencies, into a resonator that is some dispersion. You get this filtering effect of the resonator. How does that describe by the Lugiato-Lefever equation? Well, you may notice that in the Lugiato-Lefever equation, beta 1 doesn't show up, okay? So we have somehow it has been factored out, and it's factored out. In fact, it's already factored out in the Nonlinear Schrödinger equation by using a traveling reference frame. You actually follow the pulse, and that's how you describe the time across the pulse. So beta 1 has disappeared long ago, which means that if we forget about beta 1 and we plot the position of these lines again, this is why they will fall up, okay? we remove 2 pi for the first resonance, we remove 4 pi for the second, 6 pi from the third, so they all sort of aggregate around the central resonance. And now you can see that with a single resonance, if I factor out the beta 1, I can actually correctly describe the fact that these frequencies are filtered out by the resonator. I don't need multiple resonance, okay? Now, there's a bit of a catch here in the sense that you can see that this one is at the resonance, this one is slightly down, slightly down, slightly down. This one goes up here because I'm starting to climb up to against the next resonance. While here it keeps going down, okay? And so this is the limit of validity of the Lugiato-Lefever equation. If your spectrum is broad enough that the dispersion effect is starting to push, say, the nth mode close to the n+1 resonance, then that is not captured by the LLE model, okay? But in practice, for micro-resonator frequency comb, you work far away from those limits, okay? But yeah, that's the sort of full picture, if you like. Okay, just to, I'm not going to explore all of that, but this is the equation I've been describing. In the micro-resonator context, you may encounter this equation, which is basically, it has exact mathematical structure. It's just different notation in terms of power here. So E squared is the power here. Here, B squared is the number of photons. There is a relation between gamma and G, you know, because of this different scaling. Here we have the loss, kappa is the line width. The phase detuning here is replaced by frequency detuning. And the dispersion, in terms of having beta 2, we have this D2 coefficient. And the relation is here, is that this coefficient D1, D2, it's a Taylor series expansion that gives you the resonance frequency in terms of the mode index. While with the beta coefficient, you get the mode index in terms of the resonance frequency. So again, it's kind of a reciprocal way of describing things. But the structure of the equation is exactly the same. Okay, if you can simulate that one or that one, you can simulate the other. It's just a rescaling. Okay. The other difference, then here, the structure along the resonator is described in time. Here is described versus an angular position along the resonator. Again, it's just a matter of scaling. So. Yeah, I'll skip that. This is one way of normalizing the Lugiato-Lefever equation, so I'll move on there. Again, if you go back to the old days of spatial diffractive cavities, they have the same equation, except that the second order time derivative was a second order spatial derivative, or even a two-dimensional Laplacian if you have 2 dimensions. But same equation structure. Okay. Something interesting to notice in the normalized form of the equation is that nothing depends on the length, nothing depends on the side of the resonator. And so this equation equally applies to a 100-meter long fiber resonator, like I studied my PhD, and to microscopic resonator. Okay. Where the lengths come into the picture is when you start to worry about boundary condition, of course, and also if you start to worry about high order dispersion for broadband comb, for example, then you start to get some difference, things that depends on the length. But at first order approximation, when you look at the basic cavity soliton, it's exactly the same physics in 100-meter fiber loop than in 200 micron resonator or micro resonator. Another form of this equation which you may encounter is the following. It's obtained by doing this change of variables. So instead of having a detuning, you have your driving term, which is temporally oscillating. And this is referred to as the AC-driven nonlinear Schrödinger equation. But again, it's the same equation. Okay, it's just a different sort of scaling. So, what can we do with this equation? Very quickly, how much? Well, 28. I have till 1040, is it? Something like that, yeah. So if we solve for the, if we ignore dispersion, where's my pointer? If we ignore dispersion and we look for stationary solution, so this is like looking at the Fabry-Pérot, but including the nonlinearity, you can find this relation where y here is my normalized intracavity power and x is the normalized driving power. You know, y versus x, power versus driving power, easy to remember. And you can see it's a cubic relation, and so depending on the detuning, you get these hysteresis curve I shown before. So it's described very nicely as a simple cubic polynomial. It's very easy to solve with a polynomial root solver. You can predict the position of these turning points here, which again shows you that bistability only exists if the detuning, capital delta, exceeds a certain value, as I've shown you before. You can also notice that in terms of the detuning delta, this is a second order polynomial in delta, so you can easily solve for delta. And this basically describes the tilted resonance there using this simple expression there. Okay, so I'll skip those parts. So I go to modulation instability. Martin introduced that, you know, because of the K nonlinearity. If you have some strong pump, some driving term, parametric forward mixing, the K nonlinearity generate these sidebands and they start to grow, and it creates this modulation, which is the sort of the root cause of Combs, of course, right? In microresonator, I mean. I'll skip that a bit. Something to keep in mind again, this has been studied in the spatial domain far before all of that. You know, you can see this paper from 87 and 94. So again, this was a two-dimensional planar cavity with K nonlinearity. You can see these two-dimensional patterns, spatial pattern, that is the equivalent of having a temporal modulation, which is what these sidebands describe in the time domain, okay? So there's a lot of previous work available in the literature. So to study this mathematically, again, I'll do that quickly. This is nicely explained in this old paper. You take your field as being the solution that I've just shown here, okay, the solution to this case, okay, the continuous wave solution where there is no dispersion. You add two small sidebands detuned by omega and minus omega. You assume they are small, so you put that into the equation, you linearize it. You get a linear system of a matrix, you calculate the eigenvalues, and the eigenvalue tells you the rate at which these sidebands evolve, okay? And for them to grow, to observe this instability, this eigenvalue needs to have a positive real part. And then if you do the math, you find that there's two conditions. First of all, you need to have y larger than 1, because we have minus 1 plus something here. For that to go past 0, the square root needs to be at least 1, right? And remember that y is my intracavity power, so it shows that there is a threshold of power to observe this behavior. This is like the threshold of a laser, okay? The second thing you can do is that you may wonder, okay, what is the frequency at which this instability is going to appear, which is the frequency for which the real part is going to be the largest. And you find this relation, and obviously omega square, which is a square, has to be positive. And this gives you another condition on the intracavity power, which this time depends on the dispersion, whether it's normal or anomalous. So eta here is the sign of the beta 2 coefficient, is +1 or -1. The slides are available. You can read that casually at home tonight when you fall asleep. So something interesting to notice here is that it's modulation stability in the resonator is possible with normal dispersion. I don't know if Martin mentioned that, but if you just take the nonlinear Schrödinger equation, you only get modulation stability with anomalous dispersion, while here it appears with normal dispersion. And so that's kind of interesting. And there's been some earlier work, Nakazawa in 1989, they tried to have modulation stability in a sort of a laser configuration, which has exactly a resonator like that, but very low finesse. And they describe it as like a laser, you know, there is the modulation stability gain and the loss, and there is a balance, and then you can get the lasing effect. But it's a bit more complicated than that. The fact that we can get modulation stability with normal dispersion shows that the picture is more complicated, because it's not just the gain of the nonlinear Schrödinger equation that's entered into the picture. The cavity is doing something more. Okay? And you can see that by, if you look at this equation and you put back into the normal units, the real units, I mean, this looks like a phase matching condition. For modulation stability to occur, we need a balance between the dispersion-induced phase shift, the nonlinearity-induced phase shift, the self and cross-phase modulation, and the cavity tuning, okay? And you can see that because of the cavity tuning, it's possible to satisfy this equation even if the first two terms are positive, okay? So even if beta 2 is positive. While if you have the NLSE only, delta naught is not there, beta 2 has to be negative. And the other interesting thing about the resonator configuration is that in the NLSE, when this modulation stability appears, you know, the modulation appears and then it disappears. It appears and disappears. There's this breathing, which is called the Fermi-Pascal-Ulam-Tsing-Hu recurrence, very famous stuff. In the resonator, you know, your sideband are getting some gain, but then the power is lost through the coupler. And so at some point there is a balance between this gain and loss, and you can get these stationary patterns. Like, you know, the patterns on the zebra, they're stationary. They don't come in and out, okay? Again, that's a difference between the two, the cavity geometry and the sort of yeah, it would be cool to have a zebra like that. So just looking at this condition for the occurrence of the instability, if I go back on this diagram, this is my tilted resonance. So this is power, intragravity power versus the tuning. This is sort of the hysteresis curve. This is intragravity power versus driving power, but again, there are sort of two different cross sections, okay? For normal dispersion, modulation instability appears in this sort of orange region, and so it actually appears at the end of the bottom branch here, okay? You may hear sometime in the microresonator context that there is no modulation instability in normal dispersion, therefore you need mode crossing and blah, blah, blah to get something, but it's not strictly true. There's a tiny, tiny region of modulation instability here, which is not easily accessible. I accessed it in my thesis, okay, and even like that, it was only very transient. This is a measurement of the spectrum over time. You can see the sidebands growing there, but then very quickly the system destabilizes, you jump to the upper branch, okay. In the anomalous dispersion regime, you have a much wider region where modulation instability is possible. And in particular, you can see that if you're probably familiar with the idea that we need to tune the laser frequency towards the resonance. Well, if we do that, I'm starting from the left here, I tune my laser, I enter this region, modulation instability occur. This is the start of type 1 comps and the like, okay? And so this is where this comes up, okay? And it corresponds to being on the top branch there. Again, you might think that this was only observed with microresonator and the like, but no, there was somebody in the past, it's called Stéphane Coen here, who observed that in a 100-meter fiber resonator. And, there was only a few sidebands, but in retrospect, we can actually call that a macro resonator frequency comp if I dare. To be honest, it's probably lots of super modes in there, and it was probably very noisy and so on. So I can't really claim that I made the first frequency comb in a resonator. And definitely we didn't correct the noise and so on, okay? For those of you who attended Koala, you may see that I'm still using the wrong minus sign there, but yeah. These are hyphens, these are not minus. And yeah, when micro resonator came along, then these sidebands are generated through that process. Okay. So you may have heard about type 1 combs. When you get this modulation instability, you typically find that the peak of the gain, the frequency at which this occurs, is a multiple of the free spectral range. Okay, and this in the time domain, that means that we have several periods of the modulation across a single round trip. Okay. And these are called the type 1 comb. Okay? The problem with type 1 combs is that this picture is a little bit more complicated than that, is that very quickly as you sort of push the system towards the right here, the pattern, this modulation instability pattern destabilizes, starts to breathe and be chaotic and so on. And so, so that's not very nice. So how can you, and this was typical of early experiment with microresonator frequency comb. This is a 2011 one from Alex Geiser's group. And if you try to simulate it, if you do sort of you see that it's moved all along like that. But if you do the average of the spectrum, which is the red line, you can see that it's actually matched reasonably well. So this was probably something like that back in 2011. Okay. How can we stabilize things? Well, one way to stabilize is to ensure that your modulation sidebands falls at 1 FSR. Okay. But the only good way of doing that is to use very small resonator, which is like terahertz free spectral range, not necessarily a nice thing. But it is probably what happened in that 2007 experiment. Okay. The other way is to use the so-called cavity solitons. Okay, and I think I still have like 10 minutes or 8 minutes. So you're familiar with this idea that we have these patterns that appear through modulation instability, and they exist within this orange region. Well, if you look a little bit further in the orange region, in particular, sort of past this point here to the right of that point, we can have the pattern. This is the orange region, but at the same time, we can have the low power solution that's at the base of the. This is basically the lowest state of the bistability here. So we can have a coexistence between the pattern solution and the lower state solution. We can have a solution like the green one, okay, which in the sort of a Prigoghine's terminology is what he referred to as a localized dissipative structure. It's a periodic structure. It is dissipative, there's loss, but it's localized. Okay, it only exists for a certain region of space or time in this case. Okay. Now, if you push things a little bit further, why not having a single period of the pattern and connects it to this solution, okay? And this is what the cavity soliton, or they're also called dissipative Kerr soliton nowadays. I'm not quite sure why Tobias Kippenberg introduced a new name, but because some people may think that dissipative Kerr soliton started in 2014, in that first publication of Kippenberg group. But that I've said, there's all the optical fiber works and the spatial system before, and all of that is basically the same physics, okay? So these exist, in this blue region, because we need to be in a region where the modulation stability, which is the orange blob, overlap with the lower state, yeah. Nothing, once you connect to the pattern for a single period, nothing prevents you from connecting another time and a third time to the pattern until you can have arbitrary number of solitons at arbitrary position. And that's why when you excite combs, you can have n solitons. These solitons are essentially independent. They can be turned on and off at will, okay? It's not like a mod-lock laser, which is necessarily periodic. It's a very different sort of types of physics. So if you look at, in terms of soliton, Martin explained that there's this balance between dispersion and nonlinearity in the nonlinear Schrödinger equation. In the resonator contact, there's this additional balance between the driving, the power that's coming in, and the loss, the power that's coming out through to the coupler. And because of that, the soliton are attractors, okay? You cannot have soliton with different power level. There's only one power level where you get this double balance, okay? So that's a bit of a difference as well. And these are some, you probably have seen temporal cavity soliton before. They have a shape like that. The background here, there's a bit of a dip around. And these are some, this is the hysteresis curve I shown before. This is the homogeneous solution. And on the same graph here, I've plotted the peak power of the soliton for various driving power. You can see it varies, okay? And this is the width of the soliton again. And this is the phase profile. It's not, usually we don't plot the phase profile. It's not very interesting, but here you go. If we do different tuning, then we get different curves. So this is all very good. So these are some, you probably have seen that, or you may have seen that. There's the first observation of a cavity soliton or a dissipative Kerr soliton. It was done in optical fibers in about in a 300-meter resonator. That was 2010. 2014, of course, the soliton was observed in the micro resonator. But, credits where credits is due. First cavity soliton were observed in 2002 in these planar cavities. So the image is kind of inverted here. The black blob is where there is this high intensity, two-dimensionally localized pulses. Not pulse, pulse, but it's a spatial peak, okay? This is X and Y here. And you can see they can turn it on. There's one peak. They can turn the second one on. The first one is happy. Then they can turn off the first one. The second one stays. And these blobs there is because the planar cavity is not exactly planar and there are defects and so on. So. 3 minutes. Yeah, I think we can do this. This is the spectrum of a cavity soliton. The spectrum is kind of easy to interpret. We have this large triangular thing. This is the peak, okay, which is typically close to a hyperbolic sequence. So we get these linear wings on a logarithmic scale. And then we get a peak in the center. That's your continuous wave background, your DC field on top, okay? So that's why the spectrum is that shape. We did a frog spectrogram of a cavity soliton. I'm not sure we actually published that, but they look a little bit funny. You get these, so frog is a frequency here on the vertical axis versus delay. And you can see we have these sort of hyperbolic shaped fringes. That's because when you do a frog, you take your pulse, you make a second copy, you send that into a nonlinear crystal, it makes the product of the two, okay? If there's no background and you separate the pulse by more than the width, when you do the product, you get 0, okay? But here we have the background. If we separate by more than the width, we get 2 copies of the pulse, and the spectrum of 2 copies of the pulse are spectral interferences, okay? And this is what you see here. And as you introduce larger and larger delay, the fringe get closer together. And so that's why we get these sort of patterns there. It's kind of cool. And this is also, I think it's a very unique measurement. I think it's the only direct temporal measurement of an optical soliton using an optical sampling scope. So this is not derived through frog. It's a direct intensity measurement. And you can clearly see the little dips and the background there, which I think is quite cool. Just to finish, There's some complication as usual. You know, I've told you the soliton exists in this blue region here. Well, on the left side of this blue region, we have these so-called breathers. Okay, the soliton is unstable; it's breathed. Again, it was observed in optical fibers before it was observed in microresonator. I think you got the message here. A lot of work was done before microresonator. The breathing can be regular. It can also turn irregular. Basically, the further you push to the left of this dark blue region, the more regular it becomes. These are measurements by Miles Anderson, who is somewhere here, I think. Here we go. He did that in Auckland when he did his master thesis. And eventually it turns chaotic. So in this diagram, what we have here vertically, it's time, okay? Horizontally is the measurement along the resonator round trip. We start with a soliton that's breathing a little bit, it's turning on and off, and then you can see it's spread out. It's basically turning into a chaotic pattern as I've shown you before, okay? And so this exists in this region, okay? And so just to sum up what we have this orange blob, which is the region of modulation and stability. We have this unstable modulation stability region, unstable soliton, stable soliton, okay? And so that's why when you tune your frequency to generate your microresonator frequency comb, you come from the left here, the pattern, the modulation stability appears here, it becomes chaotic, and eventually turns into the soliton. But because of all these chaotic behavior, as you know, you may end up with several solitons and so on, and you need a special number of tricks. So this is, I think, an early numerical simulation of that detuning scan. So you may need some tricks to have only a single soliton. So, but that's where it all comes from, really. I'll skip there. This is here we go. So this is to show you that what looks like a simple thing can be actually quite complicated. Thank you.